All right, recording is rolling. Welcome to Monday, September 18. Got a new week lined up here. All right, so we're gonna spend most of class going over these chapter 4 puzzles, or at least as far as I can get you guys. All right, so I'll do some of those guys with you guys. All right, so here, let's go bottom to top this time. Make these different, switch things up. So AP Classroom for Unit 2. You guys remember AP Classroom? So this is due 1 week from now. I want you guys to have this finished by the time you guys come back in on Monday, so we can take that Monday and go over the solutions for Unit 2. Okay. Right. These particular puzzles we're going to go over today aren't due until like almost 2 weeks from now on Friday, so you guys got enough time there. Right, quizzes. Right, projectile quizzes. If you turn those in back on Friday, then I got the graded over the weekend. I'm still waiting for a few more. There were a few students that were absent. So yeah, we have to turn those in. Right? And then once I get them all, then I can go back to guys. You guys can do corrections if you like. All right. So technical details here. Hold on. I'm going to pause this real fast. All right. Recorded is resumed. So some details. Right, so you guys know one of the big concepts in this class, one of the important takeaways are graphical relationships. And a pretty common graphical relationship is something like this, something that's parabolic. For example, when you guys were rolling cars down inclines, you were saying, what's the relationship between how far it rolls and how much time it's been rolling for? That was one of these type relationships. It was like how far was proportional to the time squared. Right? So let's see if you guys are following. So suppose you let the car roll for like 1 second and it rolled so far. Then you go back and you let it roll for 3 seconds. Ooh, that's 3 times the time. How many times the distance would it roll? 9 times. Because 3 times the time is like 9 times the distance. Right. That's one of these parabolic type relationships. If you graph distance versus time, right? Get a parabola. Right? Or distance versus time squared, it would straighten out to a straight line, right? Right. Now, a lot of times I'll ask students, okay, what kind of relationship is this or that? And a lot of students say this term here. They'll say, oh, that's exponential, which I can see why you'd say it because there is an exponent, right? But an exponential curve is actually a completely different class of curve, right? So it's a little technical thing, but let me show you the difference in what we're talking about here, right? Exponential curves you will almost never see in this class. I don't think they show up in any labs that we're doing here at all. In the real world, you'll see this with like interest rates, right? If you have money accumulating interest rate in a bank or inflation for that matter, it could go like this. You guys know Moore's law, like the number of transistors you can fit economically on a computer chip like doubles periodically, or at least has for many decades, right? Those are all exponential type curves. Okay? But in this class, when you're with your guys' labs, looking for something like this. Okay? So here's the difference. Like if the variable is raised to a power, like x squared, right? That could be like a parabola. Right? Some of this exponential is where the variable is in the exponent itself, right? So let's throw in a number. Let's say you pick like 300, right? So what if x is 300? 300 squared, what's that? Okay, so it's like 90,000, right? Okay, so that's a big number, right? 90,000 is a big number, right? I guess it would have better context if having a unit attached to that. What are we talking about? 90,000 meters, 90,000 newtons, milligrams, right? Now, what if you swap the base and the power? What instead of doing 300 to the power 2, what if you do 2 to the power 300? So let me ask you guys, which number do you think is bigger? 300 to the power 2 or 2 to the power 300? How many guys say 2 to the 300 is the bigger number? Bigger number. Ooh, is that everybody? Almost everybody? Everybody? Right? Right. How much bigger? A little bit bigger? A lot bigger? Guys, 2 to the 300 is like the number of atoms in the observable universe. Yeah. So that's like wildly different, right? Yeah. So this curve blows up real fast. Right. Right. Oh, another technical detail. Okay, this is gonna matter on like AP FRQs if you guys are doing write-ups. Right? When I say gravitational force, suppose like here I got 1 kilogram here. This is 1 kilogram of mass. Right? And then if I pick it up, ooh, now I feel a downward force of like 10 newtons. Right? So I'll call that weight or force due to gravity, something like that. Right? Now I'll ask students, what force is that? And then the most common answer, like far and away, is gravity. Right? Right. Now, I don't mind that. It's like, okay, I know exactly what you're talking about. But okay, this is like one of those technical things that could lose you points on an AP exam. Don't call the force itself gravity. I don't know, just a thing, I guess. Right? You can call it weight. You can call it force due to gravity, and then they'll give you the points. But if you just write gravity, then if they're a real stickler, they probably won't give you the points for that. Okay. All right, so you guys get there? All right. Let's switch over to these puzzles. All right, I want to get you guys this far as I can on these. No, I assigned quite a few. So here's what I do is solve these, but just change the numbers so you guys have a little bit more practice here. All right. This whole first page is under a category in your book called warm-up exercises. Okay, so that's nice. Warm-up. Warm-up number 2. 4 forces act on an object. We got an east force, a north force, a west force, and a south force. Right? What is the magnitude of the net force, and what's the direction of that net force? Right? So this could be warm-up number 2. Right? Suppose you have a soccer ball set in the middle of a field, right? And 4 kids come up to kick it at the same time. 1 kid kicks it north, 1 kid kicks it south, 1 kid kicks it to the west, 1 kid kicks it to the east. Right? Well, there's some like cumulative effect. There's a net effect, as if there was a single force, right? As if there's like a single kick. Right? Well, what's that going to be? Right. So let's get the soccer ball in the middle of the field. I'm going to do a free body diagram like I've been telling you guys to do it. So put a center mass dot and then draw the forces extending away from that. Right. Outward from that point. Right. Right. So we're going to make up something. What if the north kick was like, 100 newtons? The south kick was like, let's call it 60 newtons. Let's have the east kick be like 180 newtons. And let's have the west kick be like about 150 newtons. Right, something like that. And just big crazy numbers, right? Okay, so 4 kids kick the soccer ball, bam, right? What's the net effect? Right? But just eyeballing it, looks like the upward force is going to beat the downward force, and I should say the north is going to beat the south, and the east is going to beat the west, kind of deal. Right? So it should be head off kind of northeast-ish is what I'm thinking. Right? But that's what we did. So let's just systematically. I want to say, what is the sum of the forces in the x direction, and then later on, what's the sum of the forces in the y direction? Right? That's also called the net force in the x direction. Right? So the sum of forces is the net force, right? Sigma is the sum of, right? Sum of, right? Right, so for us, that's going to be 180 newtons to the east, and then subtract 150 newtons to the west, right? Which gives 30 Newton force to the east, like eastward. Right? Now that's just one component of the net force, right? So that's on the east-west axis. Okay. Now let's try north-south. What is the sum of the forces in the y direction? Okay. Well, I've got 100 newtons to the north, and subtract off the 60 newtons to the south. Is that going to give us, what, 40 newtons to the north? Okay, so then I dash outline that. Okay, you guys see that? So net effect, net effect. Okay. Now let's put it all together. So I'll go back to the soccer ball. Say, it's as if there's a single force on the soccer ball. Maybe I'll dash it. How about that? Going 40 newtons straight north, right? And it's also as if there's a single force, 30 newtons straight east. I'm going to connect this tip to tail. See how I'm doing like vector components and I'm attaching tip to tail? 30 newtons right there. You guys see that? Tip to tail? Because I'm trying to add these vector components together. Okay? So here's going to be the resultant. Or I should have asked you guys, what's this vector called? It starts with an R. You guys would have said resultant, right? Okay. That resultant has a magnitude and a direction, right? Oh yeah, and it is like we suspected from the very beginning. Remember, just like helicopter view, just eyeball it. Said, okay, well, overall to the north, overall to the east. Right now we got to quantify it. Boom, boom. Right now we're getting down near the end. It's definitely going something about northeast, right? What is the resultant? 50 newtons. Ah, how'd you guys know it was 50 newtons? Yeah, this does happen to be a 3, 4, 5 right triangle. I don't know if your book numbers work out so nice, but maybe, right? Yeah, so systematically, you could do a Pythagorean theorem. So square root of 40 squared plus 30 squared, right? Square root of all that, and then newtons, I could just take the unit out. And you're right, that would be a 50 Newton magnitude force, right? One more detail, I want to know something about the direction. Maybe I'll call this theta. How about theta? Okay. How can you quantify theta? Yeah, inverse tan, right? Remember, so in inverse trig, you can like undo ratios to solve for angles. Okay? Inverse tan. Now, if I do inverse tan, that would be whatever what. Yeah, 30/40. Right? Newtons cancel out anyway, whatever. Okay. Oh, and some of you guys might possibly have this one memorized by this point in the class because I set you guys up a special triangle, right? How many degrees is that? About 37 degrees? Ah, okay. So I'll take this 50 newtons, and this would be at 37 degrees east of north. Right? Bearing is usually reported like with respect to a north-south line, so like east of north. Good, right? Like I said. Okay, so there you go. There's the full answer. Okay. You guys have different numbers in your textbook, but it's the same idea. Okay. Guys good? All right. Number 4. Zoom in here. Number 4. What would the acceleration of gravity be at the surface of a world with twice Earth's mass and twice Earth's radius? Okay, I didn't realize until I started solving this one earlier today, but this kind of gets into future content, right? The book and AP's curriculum are not 100% aligned, so we're going to look a little bit into future content. I didn't mean to do that. I just caught that today, but we'll go ahead and do this one anyway. Right? So you guys know what Earth's gravity field is. Like if I drop something, it's accelerating at how much? Yeah, 10 meters per second squared, right? It picks up 10 meters per second every second it's been falling, right? That has something to do with how massive is the Earth and like what's the radial size of the Earth kind of deal, right? But let me go ahead and give it to you. This is from Unit 3 by AP's book. It goes, the gravitational force, right? Ooh, look at that, force due to gravity. Now, normally I just call that M times G, mass times gravity field, but you do like that, right? Is equal to what's called the universal gravity constant, right? This is a special number, about to show you guys anyway, times the mass of the planet, times the mass of the object that, well, I guess is under that influence of gravity, so it could have some weight, right? All divided by the radial size of the Earth squared. So if I like draw the Earth, this could be like the Earth. The Earth has some radial size I'll call capital R, right? And then at the surface, there's some gravity field, right? Now, you guys know, Newton's second law of motion. If you take a force and you divide by mass, you get an acceleration, right? Sometimes I've been calling this just plain N times G. Actually, that's how we usually write weight, right? Just N times G, but it's a force due to gravity, right? Let's divide everything by the mass of some object that could be at the surface. So if you do that, wouldn't you just very simply get the gravity field is universal gravity constant times the mass of the planet, mass of the planet, all divided by the radial size of the Earth squared, something like that. Okay. And just to show you that this does work out, let's do the gravity field for Earth. Okay, here. So this universal gravity constant is a tiny, tiny number. It goes 6.67 times 10 to the negative 11. Guys, negative 11 power. That means it's a tiny number, right? It's like 0.0000. It's like a string of zeros before you hit anything. And Newton meter squared per kilogram squared. Okay, again, you guys probably won't see this for another few weeks, and then it'll come back. But the mass of the Earth is like 5.98 times 10 to the 24 kilograms. I think it's on one of my posters somewhere. Okay. And then divide by the radial size of the Earth is like 6.38 times 10 to the 6 meters, right? And then we're going to square that. Okay. Now, you guys know what number is going to pop up in my calculator if I punch that into my calculator. There's only one number that could ever be. And what is that going to be? Yeah, about 10 meters per second squared, right? Or if we got some extra precision, we got 3 digits there, 3 digits there, 3 digits there, precision, right? Ooh, maybe slightly under 10. Okay, let's find out. So 6.67 times 10 to the negative 11, and then a bunch of units. Okay. 5.98 times 10 to the 24, close parenthesis, all divided by open parenthesis, 6.38 times 10 to the 6, close, squared. Something with a squared relationship there. Wonder what that's about. Well, just plant that idea today, but come back to that in a few weeks. Okay. Hey, is that 9.8 meters per second squared? Look at there's these 9.8 meters per second squared. Yeah. Oh, of course that was what the gravity of the Earth was going to be. 9.8 meters per second squared, right? Something like that. Okay, great. So we got a static value. Great. We know what the gravity field of the planet is. But what they're asking is, what if you start changing these by some proportion, changing these variables? So we're going to simultaneously double the mass of the planet. Maybe we find some new planet somewhere out in space and has double the mass of Earth, but it also has double the radial size, so it's physically larger, right? Right now, question for you guys before I start plugging and chugging. If there's a planet that's has twice the mass, but it's also twice the radial size, does that planet have the same density as Earth, like it could be made out of Earth dirt, or is it a really dense planet, like made out of lead, or is it a really puffy planet, like made out of styrofoam?
Less dense.
Less dense? How many of you guys think it's a giant puffy planet made out of styrofoam? Twice the mass, but twice the radial size. You guys think? Yeah, yeah, big puffy planet. Right here. Do you guys remember? I you guys something about scaling. Right, you guys remember scaling? Right. So if you scale something up by some factor, different physical quantities change at different rates. So we got like, well, I guess I'm showing factors of 3 here, but you could just replace this base 3 with 2. Right. So we're scaling it by factor 2. Right. So twice the radial size would be how many times the volume? What's 2 to the power of 3? 8. Right. So a planet with twice Earth's radius would have 8 times the volume, wouldn't it? Because if it's 8 times the volume, but only twice the mass, ooh, yeah, that's a big puff planet, right? It only has a quarter of the density. Right, you guys kind of see that? Right? Right. If it's scaled up with the same density, then I could also say that right, it should ideally have 8 times the mass of Earth, but only has 2 times. Ooh, right, you guys remember that scaling? All right. So let's see what we're going to do with this then. I'm going to solve this in terms of variables with you guys. I just wanted you guys to see that does work out to 9.8 meters per second squared. Let's try this out. What if I have F, whoops, scratch that. Okay. Let's call it a gravity field of planet X. Gravity field of planet X. Okay. We know that gravity field of Earth is like universal gravity constant times the mass of Earth divided by radius of Earth squared. Right? So we know that already. The gravity field of planet X, well, I have universal gravity constant times 2 times the mass of Earth, all divided by 2 times the radius of Earth squared. Right? Can that be true? Right. Right now, so the gravity field on planet X is, you can take this 2 out in front, got a 2 there. Right? Look, guys, what is a factor of 2 squared? 4. Bring that out in front. And I have gravity, universal gravity constant, mass of Earth, radius of Earth squared. Hey, this right here is this right here. See that? Right? And as 2 over 4, what does that reduce to? Yeah, half. Right, so half of the gravity field on Earth is the gravity field of our giant puff planet. Okay? Right? So I guess that would be about 5 meters per second squared, if you like. I guess this was the answer they were looking for, like in terms of proportions. Right? But if you want to tag a number to it, you call that about 5 meters per second squared. Right? And if you were bouncing around on that planet, you would feel like you had half your weight. Right? You guys got that? All right. So yeah, be ready to feel the like, scaling up and down variables, proportions, like within a larger expression like that. Right. Number 6, 2 identical strings make an angle 30 degrees from the vertical, and there's this mass with 15 kilograms. You guys know what 1 kilogram is, right? It's your large slab weight. Okay? So what if it was like 15 of those? What is the tension in each of the strings? Tension in each of the strings, right? Okay. Now the poster that's hanging in my room right now looks like that, which you guys also did in your spring scale lab, and this is where we're going with this, right? So here, if it's static, so because it's in equilibrium, then the forces have to sum to 0. And then if you introduce a Cartesian system, right, like Cartesian axes, right, you say, well, that's going to be also true along the horizontal and vertical axes. So up and down, these cancel out. So the vertical components of my spring scales on this poster have to cancel out with the weight. That would satisfy this green condition. Some of the forces in the y is 0. Okay? But also the amount that one spring is pulling to the right, the other spring is pulling to the left, well, that has to 0 out too to satisfy that blue condition. Some of the force x go to 0, right? Okay. Now this poster, it is symmetrical, just like the question being given. Right? Over last weekend, I made a little bit more complex version of this. What if it's not symmetrical? What if you have 2 different angles here? But it's the exact same principle that applies, right? So however much these scales are pulling up collectively has to balance out with the weight pulling down. So I can make a little expression, and then that could be like the first step of a larger process, right? And however much one scale is pulling to the right, the other scale is pulling to the left. You see how I made these dash components here the same magnitude to satisfy this blue condition. And then here's how it writes out, right? You guys see I got lots of sines and cosines going on here, right? And I got two different angles, alpha and beta. I got sines and cosines going on, right? You guys see that? Right? But it's the same basic principle, right? So that's the more complicated version. This warm-up question has the symmetry going on. So you could very more simply think of it more like this. Okay? But let's throw some numbers on the board and let's solve this thing. Number 6. Okay, so I'm gonna get some axes here, like a Cartesian system. Right? I'm gonna put a dot right in the middle where all the strings are coming together, which could be like this point right here, right? Where all the strings are coming together. Okay. Now let's get some forces. Well, okay. I'll go ahead and try to keep that 30-degree angle. How about that? Like that. It's pretty close, just eyeballing it. Pretty close. Like that. And then something like that. Okay. I think I got that pretty close. Right? Because if I just for this problem, since we know it's symmetrical and these angles are the same, this is 30 degrees, this is 30 degrees. Right? I'll go ahead and give you guys the simplified version. The simplified version is that these tensions are the same. So I can call this F sub T. I can also call this F sub T, right? Right? See, like if it wasn't symmetrical, then I'd have to call this the force on the left and the force on the right, and then those would be extra variables I'd have to solve for, right? But just keeping it pretty basic for this warm-up question. It's symmetrical, so they'd be the same tension. Wouldn't that be right? Right. And that's the question: is what is that tension that happens to be the same for both of them here because of symmetry? Right. Now, go ahead and do exactly what you guys see in the poster. Oh, yeah, there it is. It's hanging right in front of me right there. That poster is. Right? I'm going to break these tension forces into components. Okay? A little bit to the left and up, a little bit to the right and up. Right? Okay. This angle is also 30 degrees. This angle is also 30 degrees. Or if you like, you could play off the 60-degree angle down here. That'd be okay too. Okay. Oh, and here's the weight pulling down. Call it mg, the weight. Okay. All good so far? Okay. All right. Do you guys see that? Okay, so graphically, how I was trying to do it. Do you guys see that this upper part and this upper part could combine to balance out the weight down? Right? This, bam, 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 bam. Right? You guys see that? Right? These two guys cancel with this. That's the sum of the forces in the y is equal to 0. This horizontal component and this horizontal component also zero out. Right? So that this central point's in static equilibrium. Right? Everybody see that? Right, so I can say this leg right here is whatever the tension force is, which we're solving for, times cosine. Oh, I was going to ask you guys, sine or cosine of 30 degrees. You guys would have said cosine of 30 degrees, right? Because it's adjacent to 30 degrees. Could you call that tension force times sine of 60 degrees? Yeah, same thing, right? This is a 60-degree angle down here, if you like. A 30, 60, 90 triangle going on. Right. I think we can get it all from that because I can say this. I can say the sum of the forces in the y direction goes to 0 newtons. Right? Again, if it was different angles and we had an asymmetrical situation, I'd have to also set up the sum of forces in the x direction goes to 0 newtons. That's kind of the other important condition. But in this case, just based on symmetry, it's not going to be super revealing. Okay? So sum of the forces in y goes to 0. That means that tension force times cosine of 30 degrees. So tension force that we're solving for times cosine of 30 degrees. Right? Well, plus the other tension force times also cosine of 30 degrees. Right? Minus the weight. That zeroes out. Right, you guys see that? Is what is cosine of 30 degrees? Does anybody remember from math? It's like the root 3 over 2. You guys kind of remember that? Right? And this guy is also the root 3 over 2. Maybe you're thinking sine of 60 degrees, same thing. Okay. All right. Oh, okay, well, we've got the same thing added to itself. So that's going to be like the square root of 3 times the tension force I could add the mg over is equal to the weight. We do like that, right? So, well, I guess we got the answer in terms of variables, right? The tension force is just going to be the weight divided by the square root of 3. I guess if you're from a math class, they don't like radicals in the denominator. I could never figure out why, but you might call it times root 3 over 3, I guess. Root 3 over 3 times mg, if you like. Right? But in physics, it doesn't really matter. Right? You can have radicals in denominators. Right? I don't care. AP doesn't care. It's fine. So that'll work. Okay. Right. Now, they told you the mass of the block, and the gravity field is implied that you're on Earth. So boom, boom, you just pop stuff in. Okay. Now, remember, that general solution is really only true for the setup where I do have 30 degrees. I do have 30-degree angles from the vertical. I did plug that in. Right. So it's not general enough to field any angles, right? Just 30-degree angles. Okay. And I also have the symmetry going on. Okay. You guys get that? That's plenty close enough to the answer where you guys can get that right. Right. You guys are getting more comfortable in this class as we go on about solving terms of variables and the whole deal. Right. All right. Next, number 10, a block mass 12 kilograms is sliding with initial velocity 8 meters per second in the positive x direction. The surface has a coefficient of friction of 0.3. Right? And your textbook always gives you 3 significant figures, so right, any number you get. What is the force of kinetic friction acting on the block? What is the block's acceleration? And how far will it slide before coming to rest? Actually, that last question looks like a kinematic question. I think we're going to have to kick back to kinematic motion, right? But it's going to take us some work before we get to that point. So, so find the force. Then we're going to go through Newton's second law of motion to figure out the rate of slowing down. Then we're going to take that and figure out how far it goes. Okay. All right, let's get a free body diagram going on this one. Number 10, free body diagram. So we're going to have a block. Right. I'll have this moving to the right. So I'll give it a fat arrow just to indicate the velocity. Right? But you guys know that velocity vector is not actually part of the free body diagram, strictly speaking, right? Because free body diagrams so far only have what kind of vector? I don't care about velocity vectors. I care about what? Force vectors, right? And then in December, we'll add torques. But for now, yeah, just force vectors. You guys are absolutely right. Now, that is important context, though, to know that it's moving to the right. Because here, let's put some force vectors on this. Right? This thing has a weight pulling it down. This thing has a normal force holding it up. Right? And as long as the floor is level, then those two should be balancing out. So the sum of the forces vertically goes to 0. Right? So it's not accelerating up or down. Right? And which direction am I drawing the friction force? Right? Opposite of the motion. Right? I'll call this F sub FR, friction force that way. Right? Is that it? That's the free body diagram on that block sliding to a stop. Okay. I wonder how far it's going to go. Well, might depend on a lot of things. All right. So they gave us here. I'm going to write some numbers. Mass is 12 kilograms. Oh, they said 12.0, but here. Right. Let's assume gravity field is about 10 meters per second squared, and coefficient of kinetic friction, U sub k, is like 0.3, let's call it 0.30. But they threw on some more digits, but whatever. Okay. First question, what is the force of kinetic friction acting on the block? All right. I do have a handful of posters I want to show you guys. Yeah, I got them queued up right here. All right. So let's take a look at this one. That's, by the way, in the room. It's over there, hanging kind of by that door, that lab closet door. Right? You guys remember your 10-part lab the other day? One of the things I had you guys do was, drag a block at constant velocity across the surface. Okay? We'll do a more extensive version of this one upcoming this week. Okay? Now, as long as you pull at constant velocity, okay, constant velocity, is that an example of equilibrium? Yeah, because 0 acceleration, so 0 net force. So all the forces have to be balanced at rest or constant velocity. Those are both equilibrium. Right? So should balance out vertically, right? The weight and the normal force are balancing out. Okay? But also, whatever the spring scale force was reading, that was also telling you what the friction force was, as long as it was constant velocity, because those two have to be the same magnitude. Is that true? Right. Now, if I drag this across the surface, oops, keep forgetting that. Right. right, pulls off a constant velocity. Right. There could be different constant velocity situations depending on the materials. This is black paint, this is like regular paper, but what if this was wax paper or sandpaper, right? It might have to pull differently, right? So here's this coefficient of kinetic friction, and it's the ratio of these two forces right here. This divided by this, right? You guys see that, right? Or if you like, you can rearrange it, and you can get the friction force is equal to, you can solve for the friction force. It's coefficient of friction times the normal force. See if I just cross multiply the normal force, right? Oftentimes you see it that way. In fact, another place you see it that way is how AP gives it to you. Let's look at, you guys remember you're allowed to use this table on the actual AP exam, right? What do we got here? We got the three amigos, we got Newton's second law of motion, and we got, oh, right there, there's the fifth formula they give you. I'll zoom in on that. It says friction force is less than or equal to coefficient of friction times normal force. Oh, look, it's like rearranged, just like I was showing you guys, right? Now, a few details here. It looks like they threw some absolute value bars to indicate magnitude. So they're not talking about directions, they're talking about magnitude. Okay. Another little detail. I forget if I mentioned this to you guys. You guys see those little arrows above the F? You guys see those little arrows? Do you know what that means? The arrow? It means it's a what kind of quantity? Vector. Yeah, exactly. Right. If you ever see little arrows above these, some textbooks use them a lot, some not so much. Yeah, if you ever see a little arrow, it means vector quantity. Right. I usually drop them, but sometimes I will put them in there. Right. One other detail though, you guys see this mu, this coefficient of friction? They don't actually specify kinetic or static. And that's where this inequality is coming into play. Right. Because imagine this. Suppose you got some object sitting in the middle of the room, right, on the table. Right. You put a little tiny force. Okay, so it's not going to move because it hasn't overcome the initial friction. You push harder. Right? Look, it's still not moving. Right? Oh, so I can push with variable force. It must be that the friction force is also building up opposite how I'm pushing. Right? Okay. Oh, that's why this inequality. Right? Because it's like it's building up. But that's all for a static situation. As soon as I break the friction and it starts to move, now it's switched over to kinetic friction. Okay, and actually, I don't need as much force to keep it moving as I did to break the friction in the first place. Okay, okay, like that. Okay, and questions so far? Right, that right? Right. So I also want to show you this other poster right here. Right. Oh look! Oh, whoops! Zoom out where you guys can actually see this. Right. Hey, it's the same picture. Right. That's the same. That's the same. That's a little tiny. Right. But what are different coefficients of friction for these different type materials? Because this is like a material property, these coefficients of friction, kinetic friction, static friction, right? Right. So like once you know that this is like paint and like regular paper, it's predetermined what these values are going to be, right? So like what is like wood against wood? I know there's different kinds of wood, but maybe kind of an average value. Oh, okay. So we got like 0.3 or 0.5. That's like 30% or 50%. Remember, we're comparing these two forces right here, the friction force compared to the normal force. So this could be up to like 30, this could be 30% of this or 50% of this, depending on whether it's kinetic or static. Right, is that right? Right. See how I made this like shorter than this one? Ooh, if this is half of that, that could be like 0.5. Ooh, is that right? And I got all these numbers for these other situations. I pull this right off the internet where everything is true. Hey, look at these last three lines. We got tires versus different kinds of roads, right? What's easier to drive on, an icy road, a wet road, or a dry road? Dry, because you get like more friction going. And look at these coefficients of friction. An icy road is hardly anything, 5%, 10%. Ooh, be real careful there. Wet road, better, but the dry road is the best. Okay? In fact, I remember taking some traffic classes back in college, and they were saying this number right here could possibly get more than one, maybe like 1.1, right? 1.05, 1.1, right? Which means it would actually be easier to lift the car than it would be to like drag it across the road. I mean, right? if the tires were locked. Speaking of tires locking, when you guys got your driver's licenses, did you guys have to learn about something called anti-lock braking system? Anti-lock braking? All right, so here's how this works. Suppose you take a time machine back to the 1970s, right? You drive a car, classic car, like, oh yeah, and you got to come to a stop in a hurry. Oh no, hit the brake. What they used to tell you to do was to not slam the brake, but they said like carefully pump it. Right? But they don't say that anymore. Now they say, go ahead and slam the brake, and that anti-lock braking system that you guys learned about will take over. What it does is anti-lock braking system, anti-lock, right? It doesn't, you don't want to lock the wheels. You actually want to just let the computer system take care of this now. It's not the 70s anymore, right? We'll actually rotate the tires forward a little bit while you're trying to brake. What's that good for? Why do you want the tires to rotate forward a little bit? Which of these frictions is bigger? Static, right? It's like if the wheel's locked, you're actually skidding across the road. That's this kind of friction. That's this kinetic friction. Okay? But if the wheels can rotate forward a little bit, they can actually maintain static traction with the road. Now you're taking advantage of this kind of friction. Ooh, do you guys see consistently static friction is greater than kinetic friction? Right? Ooh, interesting, right? That's the physics of anti-lock braking. Okay. Right. All right. So now you get some good context there. All right. Now we're back to this block that's sliding to rest. Right. So we got to figure out what's the acceleration, and acceleration we're going to get. There's two perspectives you have on acceleration. You guys know it's a rate change of velocity. That's the old way of thinking about it, kinematic way. And the new way is Newton's second law of motion, net force acting on the mass of the object. Right. So we say what acceleration was and play around with the math there. Now we're going to say how you get the acceleration. Okay. Right. And what is the net force here? Is that just the friction force? Because it looks like everything vertical cancels out. Yeah, so the friction force is the net force. Right. So friction force. Right. But the friction force, well, you guys just saw. If you rearrange this, the AP version of it, just cross multiply the normal force. Isn't that just coefficient of friction times the normal force? Right. We'll give you the friction force. So that's what this is right here. This is just coefficient of, I'll call it coefficient kinetic friction times the normal force. Right. And the normal force, what do you know that's equivalent to? The weight. Right? So could that be like that? What cancels out? What cancels out? NASCAR? What does that mean? Does that mean if you have an empty car, it's just you slam the brake, come to stop in some time, some distance come to stop, right? Now you're gonna, now you got a car party. You got all your friends in your car, packed in like a bunch of clown car. You got all the groceries in the back. Same situation, same initial speed, same road. Hit the brake. What happens to your stopping distance? The same, because the mass canceled out. Doesn't matter, right? You see it? Okay. In fact, this proof I want you guys to know, because I made a poster. It's been here the whole time. Ha ha ha! Look at that. Cars are this is the same answer. Same answer. Wait, here's the rate the car can slow down. It has to do with what's the coefficient of friction between the tires of the road. It does have to do with the gravity field of the planet. Right, so I guess this would break differently on Mars. Right? But yeah, the mass of the car cancel out. Right? That's the same one we just did. I just gave you guys those notes. Right? Guess that? Okay. Well, we did a bunch of solve in terms of variables, but they did give us some numbers. So I guess let's get a number, right? Got 0.3 times 10. Can I do? So the rate that car is slowing down in this case is 0.30 times 10 meters per second squared. Could that be like 3 meters per second squared is slowing down? There it is in terms of numbers, right? Right? You guys good? Okay. What's that? Yeah. Wait, what did they ask? Did I skip past a question? I did skip past a question. Oops. Right. Sorry. Question. We just saw question B. Sorry, that was question B. Question A was what is the force of friction? So I guess that's this bit like right here, or I guess this entire numerator, right? Let's go ahead and solve part A right here. Right. So okay. So part A, the friction force would just be a coefficient of friction times the normal force, which is the same thing as coefficient of friction times the weight, as long as you have a level road, right? If it was like going up a hill, gotta be careful about that. Okay. And then friction, okay, we got 0.3, we got a 12 kilogram block, we got 10 meters per second squared. So 12 times 10 is 120 newtons. The block weighs 120 newtons. Times 0.3, is that 30? Yeah, that sounds right. 36 newtons, right? So if you like, there's a 36 Newton force, right? But we could have done it that way too, instead of canceling out the mass, right? Because wouldn't the acceleration be net force on mass, which is 36 newtons acting on 12 kilograms, is still 3 meters per second squared, right? Could have plugged in the numbers to begin with, right? but in terms of variables, we get the same thing. Okay. Right. So there you go. Plug the numbers early, plug the numbers late. Still get the same answer. Okay. All right, guys, good there? Okay. All right, so yeah. You say 36 Newton force acting on 12 kilograms gives you 3 meters per second squared, slows down. Okay. Or if you like, you're right, the mass of the block didn't matter, it would still slow down at the same rate, even if you could change it. All right, we're good. All right. Now there was one last piece to this, which is how far does the block slide before it comes to a stop? How far does it go? Okay. And for that, we need to kick back to kinematic motion. So 10 part C, how far? Let's set up a little tax VB table. Okay. I like this checklist. It gives us a big picture point of view of what variables do we have and what are we solving for. Like we just found this. We found it slowing down at 3 meters per second squared. Okay. I might even call that negative because I know it's going to be opposite of the forward direction that it's already moving in. It's slowing down at that rate, right? The net force is backwards. The question is, how far does it slide? That's that right there. The initial velocity they gave us as, wait, did they give it to us? Oh, did I not write that down? Yeah, 8 meters per second it was. Or was it? You're right. Oops, I didn't even write that down. V naught is 8.0 meters per second. Oops, right. So this was 8 meters per second, right? Do we know anything else? Yeah.
V final should be 0.
Boom. V final is 0 meters per second because it's breaking. Come to a stop, right? That could be how far it goes, right? That's like one of those hidden variables, right? They don't explicitly print the number, but think about it, right? All right. So I think this is a case for the 3 amigos, or at least one of these guys. We're trying to figure out how far does it break. And we have initial final velocity and the rate it's slowing down. Which one of those guys is going to be able to handle that? First, second, or third? So I'm here in the first, I'm here in the third. This is both kind of right. I like the third one. I'm going to use the third one. Right? The third one doesn't say anything about time. We want breaking distance, we got everything else. Right? You could use the first. Here's how you could use the first. You could use the first one. Actually, you have to use the first two system-level equations because you wouldn't know x or t. You wouldn't know this t. I guess you use the second one to solve for t. That's what you could do. You can plug out the first one. Right. So you could do it that way. I'm just going to go ahead and use the third one. It'll get it all in one shot. Yeah. Let's go. df squared equals v naught squared plus 2ax. Or if you like, say minus 2ax. Slow it down, right? So 0 goes to there. Coming from 8 meters per second, square that. Plus 2 times negative 3 meters per second squared. Or, okay, and we're trying to figure out how far. So, all right, 8,864. Guess I'll divide stuff over, divide by 6. Would that be? Would be like 64 divided by 6, I think, meters. Is that right? Oh, where's my calculator? There you are. 6. Does that look like 10.7 meters, I think? Is that right? Did I do that right? I think. Okay, you guys good? All right, questions? Right, I think we can get a start on 13. I did earlier, so let's see where we go here. Block with some mass on a frictionless table, so that's nice. Yeah, helps apply this a little bit. Okay. Connected to a second block with a different mass. So we've got a small block and a big block. We're pulling this to the right with a given horizontal force. Okay. Figure out what's the acceleration of both blocks together, and then furthermore, what's the tension connecting to the two blocks. Hey, you know what this reminds me of? You guys remember the chain gang? You guys remember scale, weight, scale, weight, scale, weight? All I have to do is turn this 90 degrees, and we got that. Right? I'll also take off a scale and a weight. Right? That's it. Right? So I bet the force that we're pulling with is going to be, it has to pull both those blocks but the tension connecting only has to pull the block behind it. So to set that tension, it's not going to be as much. Got 13. We got 16 kilograms, 16 kg. We got 24 kg connected. All right, and we're pulling with some force here, right? Of 120 newtons, they tell us. Here, I'll just go ahead and solve with the numbers. Okay? So acceleration of the system is going to be 120 Newton force is pulling on, is that 40 kilograms? I think total. Right? Is that like, is that 3 meters per second squared? Right. That answers that. The whole system's accelerating at 3 meters per second squared. I'm going a little bit fast because not because the bell here. Right? What is the tension connecting in the string? Right. There's 2 ways to get the tension. Right. One way to get the tension is that tension is causing force tension is causing mass times acceleration of the small block. Right? So the mass of the small block is 16 kilograms. I know the acceleration is 3 meters per second squared. Is that like 48 newtons is the tension? Right? The other way you could also get it is you could check the large block. Guys, what's the difference between 120 newtons, and 48 newtons? I guess I'm checking my answer is what I'm doing. Right? I don't know, whatever that net force is, divided by 24 kilograms, it better result in an acceleration of 3 meters per second squared. Right? So I'm taking my answer and I'm just checking it with the large block. Okay? So 120 minus 48, there's the bell. Right? Yeah, so it gets me 3 meters per second squared, so it checks out. All right, well, there's a wrap. So you guys have a great afternoon, and see you guys tomorrow.